Welcome to ECE 501B. This is our first lecture, and in this lecture our goals are to provide a course overview, and then we will begin with the yellow textbook of Axler, Chapter 1, and provide or start an introduction to vector spaces. In our course motivation and overview, this course you can think of as being foundational for linear system theory. And linear system theory is described or can be represented by a block diagram where we have a system. We have input signals to that system. The input signals get processed by the system and produce output signals. And there are many different application areas where this block diagram or this configuration makes sense. And in a mathematical setting or sense, this system can be viewed as a map. We're mapping one set of signals into another set of signals. And this particular signal and system structure is very common, as I just mentioned, in many different application areas. For example, if we were interested in the control application, then this block that we've labeled system above, you could think of that as arising or being a controller or the plant dynamics, or here the plant, if you're not familiar with the terminology, the system dynamics. The system itself has some dynamics in a control environment. Another application area that has this same structure of input, system, output signals is signal processing, where now the system is doing some kind of filtering or could be representing a filter. The application area could be communications. Here we could actually subdivide that system or break it down, separate it into more refined blocks or pieces. For example, we have a communication system typically is going to begin with some kind of transducer. It might then encode that signal. It might, for transmission purposes, need to modulate that signal. Then it might go through a transmission channel. Think of the airwaves or the air itself. And then once it gets to its destination, then we might want to do a demodulation of the original modulated signal. We will want to then decode what was encoded before, and it might then be yielding some audio signal through a transducer like a speaker. And in this case, you could think of these three processes being the pre-processing, and that could then represent a system. The transmission channel could represent a system. You have a signal, it goes through the air or space, and then it gets delivered to its destination, and then we have the post-processing. Another application area where you could envision this same structure of input signals, system, and output signals is in optics, where now you have the optical hardware representing this system blocks. Luckily for what we want to do, we are going to be able to put all of these different application areas into the same mathematical framework. Luckily, we can generalize and fold a large number of application areas into a common mathematical framework. Meaning we now are going to be able to abstract away from the application and go into a math environment that allows us to develop these fundamental mathematical ideas that can be applied in these various application areas. And our abstract math environment in this class will actually be linear vector spaces. And you can think of linear vector spaces sort of in two different camps. You could live in the linear algebra space of linear vector spaces, where now we are restricting attention to finite dimensions. And that's what we will do in the textbook by Axler. The other direction that you can go is to look at linear vector spaces from a functional analysis perspective. And in this case, we are in infinite dimensions. And that's our other textbook by Frank. Luckily, we can address a lot of the same concepts and ideas common to both camps, or both the finite dimensions and the infinite dimensions, and those features can then be applied to the other area. Stated another way, both domains share many features, and we will try to take advantage of what we learn from one domain to understand the other domain. And we'll spend a lot of time in the finite dimensions trying to gain our intuition and insight into that particular domain, but a lot of the concepts and ideas will carry over into the infinite dimension setting of functional analysis, and hopefully then we can utilize that strong foundation in the finite dimensional case to use it in the infinite dimensional case. In addition to studying these concepts of linear algebra and functional analysis, we're going to have the opportunity to get into the mathematical theory in a maybe a little more in-depth way, and for that reason this course will not, or I should say this course will also try to develop our mathematical maturity by not shying away from proofs. And this will actually allow us to, or this course, we're going to have some fun. We will use some interesting, and in this case, interesting can maybe be interpreted to mean fun. We will use some interesting or fun papers to connect the theory with reality. One of those papers deals with principal component analysis. And the idea behind that paper is to try to find meaning from data. The mathematical ideas that will be used in that paper are symmetric matrices, and these ideas, hopefully, this is foreshadowing what we will learn or study in this course. It uses the ideas or concepts of eigenvalues and eigenvectors, or eigenvectors or invariant subspaces, and singular value decomposition. That's one paper that will connect the theory with reality. Or another paper is maybe a little bit dated now, because with this particular football season, they are no longer going to be relying on the Bowl Championship Series, which was a way for the organization to actually rank or to select a national champion, and that was then to rank football teams, was the application. And that particular paper illustrates how it can effectively produce a consistent ranking of football teams by utilizing positive matrices. And the positive matrices simply need to work with the won-loss record of various teams, and doing that, that paper produces a very consistent ranking versus this complex algorithm used to determine the Bowl Championship Series eventual champion. Another paper deals with the Google PageRank, or which web pages are more important or more significant based on your search strings. So what are the importance of web pages? And I believe the title of that paper is something like the 25 billion eigenvector. which was related to the market capitalization when Google went public. It maybe was valued at $25 billion, Google was as a company. That particular paper obviously then will deal with eigenvectors, and maybe in particular the eigenvector associated with the largest eigenvalue, and it will have or use other matrix concepts. Those are some of the papers that will establish a connection between reality and theory that allow us to see maybe a fun application to this theoretical subject of linear systems theory. That's an overview of the course. Let's now start the first book, which is the Yellow Book by Axler, and begin with chapter 1. First, some background, and this may then introduce some terms and definitions. First, we will concentrate on two fields or sets from which we will draw numbers. And fields here in quotes, this is a math concept that you can look up and try to determine what it is that we are going to be playing with in terms of the underlying numbers that we will be using. And in this course, we will emphasize the real numbers and the complex numbers. Those are our two fields that we will emphasize. And a field is really something that we sort of have lived with without maybe defining precisely, but the real numbers enjoy a lot of properties that we just sort of assume or take for granted, as do the complex numbers. And the complex numbers will be this a plus ib, where a and b are belonging to or elements of the real numbers, and I, which I may or may not always be consistent with saying I is the square root of -1. I might start calling that J, which is maybe the notation that is used frequently in electrical and computer engineering. This epsilon is really saying, or can be thought of as saying that A and B are an element. If A epsilon r, A is an element of the real number system. And these fields, as I said, enjoy certain properties. They commute, so we have the commutativity property, meaning if A and B are both an element of F, then A plus B is equal to B plus A, and AB is equal to BA. And you can see that if A and B are real numbers. And F here is something, let me say that in just a minute, but F will refer to either in the textbook R, the set of real numbers, or C, the set of complex numbers. We also have associativity, which means that if we have A, B, and C in some field, then it really doesn't matter how you associate those with addition or with multiplication. They enjoy the property that A plus B, that sum added to C is the same as, or you get the same result as adding A to the sum of B plus C. And similarly for the multiplication. Another property of a field are the identities, where we have the two elements, 0 and 1, that both belong to F. And we have the additive identity that says that 0 added to any element A in F, and 1 times A is equal to A for any A in F. So we have the additive identity and the multiplicative identity that are true for a field. We also have the property of inverses, additive inverse and multiplicative inverse for a field. So for each A in F, and now that backward E is signifying for each, and we may define that later, but for each A, there exists, and we may abbreviate that in a minute with a new notation, a minus A that's in F, such that minus A plus A is equal to 0. And for each non-zero A that's in our field, there exists an A inverse, or a multiplicative inverse exists in the field of numbers such that A inverse A is equal to 1. And finally, we have the distributive property, which says that for all of these A, B, and C, A times B plus C is the same as AB plus AC. Those properties need to hold for elements, or a set of elements, to form a field. And some examples of fields, we just said that the real numbers, the complex numbers, and let's say the rational numbers all of those satisfy those 5 properties, and so those are fields. Can you think of a set of numbers that do not form a field? And now what you want to do is identify a counterexample of some collection of elements in a set that might violate one, only one. It doesn't have to violate all of these. You only have to show that it doesn't satisfy one of those 5 properties. And one that you might have thought of is that the set of integers let's say Z is not a field, meaning you can't find a multiplicative inverse in the set of integers. 2, it doesn't have a multiplicative inverse, and there's your counterexample. Now that was sort of an aside on the fields, or what constitutes a field. Let's go back now. We said that we are going to concentrate on two fields, the real numbers and the complex numbers, in this course. Many times, we will be able to prove results for both fields simultaneously. And when that's the case, the book may simply use F to basically signify that that result could be applied for the real numbers or the complex numbers. And it's not critical to specify in certain cases whether you're working with the real numbers or complex numbers. Again, we're trying to develop some background material, and the first thing that we are needing is a field of numbers to work with or play with. Another concept that we need to become comfortable with is this concept of a list. And a list is an ordered group of n, lowercase n, objects, where n is a finite number. And typically, our objects are usually numbers. For example, we could have a list x sub 1, x sub 2, up to x sub little n, where x sub 1, these elements of this list, could be coming from the set of real numbers or the set of complex numbers. When this lowercase n is equal to 2, we might just refer to that as a ordered pair. Our list or lists will be coming as ordered pairs. When n is equal to 3, we have an ordered triple. And we could just keep going on, but typically we just have maybe the case where n is generic, and then we say we have a n-tuple. Sometimes it gets a little bit tedious to keep listing all of those elements in the list, and when possible, we will use a single variable to represent an entire list. For example, now we might say x, and that's now a way of quickly denoting this ordered set of objects. Now, one distinction that we need to keep in mind, not only is this list a finite list of typically numbers in a field, but also we need to make sure that we are clear that a list is not the same as a set. In a list, order and repetition do actually matter. As some examples, a set, you could say that the set of numbers 2, 4, 4 is the same as the set of numbers 2, 4, and it's also equal to the set 4, 2. Whereas a list, if we have the list 2, 4, 4, that's not the same as the list 4, 2, 4, and that's not the same as the list 2, 4. So we are distinguishing between set and list. And a list, again, is a finite collection of elements, and order and repetition are allowed. We do have a list 244 being distinct from the list 424. Another concept that we want to be clear on is what we mean by coordinate, and that is simply one of the elements in that list, or an element of a list. For example, if we had a list X x1, x2 through xn, x1 is the first coordinate, x2 is the second coordinate, and x sub n is the nth coordinate. Now that we have coordinates defined, it's a little bit easier to talk about these next two operations that we want to have in order to create what will be critical in this class, which is our vector space. So let's now look at the two operations that we want, and the first is vector addition. And list addition, so we're going to have these lists and we want to add those. List addition is performed element-wise, and it's performed element-wise, or list addition is element-wise addition of the coordinates. If we had two lists, let's say list X and list Y, we could talk about the addition of X and Y, calling that Z, by simply adding element-wise the first elements in X and Y. So we have X sub 1 plus Y sub 1, X sub 2 plus Y sub 2, etc. down to X sub n, Y sub n, and that's then equal to Z1, Z2, Z sub n. We can also then talk about scalar multiplication. Here, multiplication of a list. So now we have a list. Let's say we have the list X and we want to do a multiplication. Well, we allow scalar multiplication of that list. So multiplication of a list by a scalar number. And that multiplication, let's say the scalar number is a, which is going to then belong to our field of numbers. The multiplication of a list by a scalar number is what we mean by scalar multiplication, and that multiplication is defined element-wise. By the scalar. For example, if we had a times the list x, then we simply, and a is a scalar coming from our field of numbers. It's not a list itself. A is a scalar, so this is now a scalar quantity. And because we're taking our coordinates to be belonging to a field of numbers, we can now take a from a field and scale that with a x sub 1, a times x sub 2, a up to x sub n. Now that we have those two operations available to us, we now are in a position to define what we mean by a vector space. And this is presented on page 9 of Axler in chapter 1. And the main idea behind this vector space, before we actually define it, is to sort of think of, when you think of a vector space, you might be thinking of three concepts or three objects. First, we have a set. That's one of the concepts. And now we have that set with two operations, where the two operations are vector addition, and here we're using vector in a very abstract way, vector addition and scalar multiplication. As I said, vector are all of these elements of the set, and we can now use that word vector in a more abstract way to mean more than just a tall, thin column of real numbers. So we're going to be saying something is a vector in our set, and we'll allow that vector word to mean more than just a tall, thin column. So this is an abstract usage of the word vector. So we have three concepts that come to play to create this vector space. We have a set, and on that set we allow two operations of vector addition and scalar multiplication. Now we are ready to define the vector space, and this will look somewhat similar to some of the properties that were enjoyed or needing to be satisfied for a set of numbers to create a field. Here, for the definition of a vector space, any set V of lists, so think of X and Y and Z, so now any set that has the following properties will be a vector space. So we're defining the vector space by it satisfying the following properties. First, we want each of these set of lists to be closed under addition if it's to be a vector space. By that we mean x plus y, or the vector sum of two lists in that set, need to remain in that set V if x and y were originally in V. So our vector space is closed under addition. We add two elements from that set, and we aren't going to leave that set. That set is also closed under scalar multiplication. Again, if A is a scalar coming from a field of numbers and we scale a vector in our set V, then if X is in V and A is coming from our field of numbers, then the product of that scalar times the list keeps that new quantity AX in our set of vectors V. So those are two basic pieces or properties. It needs to be closed under addition and closed under scalar multiplication. And once we have that, then we can start talking about, is this set of vectors, does it satisfy the property of commutativity? It's a big word. So commutativity just means that the order of our vector sum does not matter. X plus y is equivalent to y plus x when x and y are both coming from the set V. So not only do we have commutativity, but we also have associativity, which says it really doesn't matter the way we associate these sums, if we're summing 3 or if we're forming the product with a couple of scalars and a vector, it's going to give us the same result. So that now we could combine x and y and then add to z, or we could combine y and z and then add to x. We have associativity of addition, and we have associativity in scalar multiplication, where AB times x is the same as A times BX. It doesn't matter how we associate those two scalar multiplications, and in this case we are assuming that x, y, and z are belonging to V, and our A and B are coming from some scalar field. We also want the vector space to have an additive identity, which just means that it has a zero vector, such that 0 and x are both in V, and when you add 0 to x, you get x back. So we have the additive identity property. We also want to have the multiplicative identity, which means that we have let's say the scalar 1, when multiplied by any vector x, will return that original vector x, where x belongs to the vector space V. We also want to have an additive inverse, which means that for every x that belongs to our vector space V, there exists a y belonging to V such that when we add x and y, we get the 0 vector. So for every element in our vector space V, it needs to have an additive inverse in the vector space V. And finally, we want to have this vector space possess the distributive property, which means that we can add x and y and then scale with the scalar a via scalar multiplication, and that's equal to a times x vector summed with a times y, where x and y are in V, or elements of V, and a is an element of our field of numbers. And we could have two scalars whose sum then distributes, so that we could add the two scalars and then use them to scale the vector x, or we could scale the vectors x, or scale the vector x with a and b separately, and then add those to get the same quantity. If we have a set of lists that are closed under addition, closed under scalar multiplication, we have this commutativity property, we have the associativity property, we have the additive identity. It has the 0 element. It has a multiplicative identity. When you hit x with 1, you get x back. Every element has an additive inverse, and the distributive property is satisfied. Then we can have a vector space. Let's now look at some examples of vector spaces so that we can then connect these maybe abstract mathematical concepts to something that we're maybe very comfortable with. One vector space, V, could be this n-dimensional vector of real elements, r to the n, where r is this sort of fancy-looking capital R. That's now, and it has a superscript of n. This is an n-dimensional vector, and each element in that vector come from the set of real numbers R. We also have the vector space of n-dimensional vector where each of the elements are complex numbers. So this is now c to the n, where n, little n, is the superscript. This is now an n-dimensional vector with elements in C. We can also have V is actually a vector space of matrices that are m by n, and each of those elements are coming from the set or the field of complex numbers. So this vector space now is a set of m by n matrices with complex elements. And now, because the elements of this vector space are referred to as vectors, now we can actually say that that matrix, that set of m by n matrices, we could call those matrices vectors. Maybe that's a little bit confusing, but that's why I'm trying to call that out. We can call these matrices vectors since the matrices are elements or objects of the vector space. Those are some fairly straightforward examples of vector spaces. We have the n-dimensional vector of real elements, we have the n-dimensional vector of complex elements, and we have this matrix m by n, set of m by n matrices with complex elements. That also forms a vector space, and each of those you can show is closed under addition, closed under scalar multiplication. It has a commutativity property, it has an associativity property, it has an additive identity, there's a multiplicative identity, it has an additive inverse, and it satisfies the distributive property in all three of these cases. And we will pick up with some more maybe a little less intuitive examples of vector spaces in the next lecture, and we'll move on from that point.